discriminant is positive, everything's okay. It's stable and overdamped. But we still need to see if the discriminant is positive or negative. So let's look at the discriminant. So that's T1 plus T2 squared. Let's write out the discriminant. So that's T1 plus T2 squared plus K1 over K2 T1 squared plus 2 T1 T2 K1 over K2 T1 squared minus 4 T1 T2. So what I did is I took this thing squared plus this thing squared plus twice this times this. Did I put the 2 in? Plus, no, I didn't do that, right? Plus 2 T1 plus T2 times K1 over K2 T1. So it's this thing squared plus this thing squared plus twice this thing times this thing minus that. Okay, and remember, all these quantities are positive. K1, K2 are positive. That's how I set it up. And T1 and T2 are positive. All right, so let's notice that T1 squared plus T2 squared, this thing is T1 squared plus T2 squared plus 2T1 T2. And this thing is minus 4T1 T2. So I have T1 squared plus T2 squared plus 2T1 T2 minus 4T1 T2. 2 minus 4 is minus 2. T1 squared plus T2 squared minus 4T1 minus 2T1 T2 is just T1 minus T2 quantity squared. So this thing is just equal to T1 minus T2 quantity squared plus K1 over K2 T1 squared plus 2T1 plus T2 K1 over K2 T1. And this is positive, and this is a perfect square, so this is positive. So this is all greater than 0. Okay, so what can we conclude from that? The discriminant is positive. So therefore its square root is real. And the magnitude of this is smaller than the magnitude of this. So therefore, the s's are both real and negative. Since they're both real and negative, the system is stable and up and down. And overdamped, sorry. Overdamped meaning things just decay exponentially. There are no oscillations and they decay exponentially. It's exactly the kind of system we like. However, the roots, that is these s's, these s stars, are not the same. Remember, in the non-interacting system, the s stars, recall, in non-interacting, s star 1 and 2 will just equal to minus 1 over T1 and minus 1 over T2. Here, the S stars are not equal to that. The S stars are different. And let's see how different they are. Any questions so far?
Yeah, good question. You said T1 minus T2 squared is a perfect square. So what does it mean? Why is it always possible?
Okay, T1 minus 2 quantity squared, because the whole thing is squared, it's always non-negative, because it's something squared. Is that enough of an explanation? You know, if T2 were bigger than T1, I would have minus 5, let's say, but when I square it, I get plus 25. Other questions? Again, it's always valid question to ask why you do what you're doing any given step. That's an important question if you're not sure. So let's examine S1 star and S2 star. So let's examine S1 star and S2 star, and let's call them theta 1 and theta 2. Just so I don't have to carry around the 1 and the star. So I don't have to carry around the star. So this equation, the denominator, so rewrite the denominator as 1 plus S theta 1 times 1 plus S theta 2. Because when I multiply it out, I'll get 1 plus theta 1 plus theta 2 S plus theta 1 theta 2 S. So I would get a quadratic where the roots are minus 1 over theta 1 and minus 1 over theta 2. So this is just, call theta 1 equal minus 1 over S1 star, and theta 2 is 1 over S2 star. So this is just another way of writing it, and I would like to relate the thetas to the t's. So let's try to relate theta 1, theta 2 to T1, T2. That's our goal, immediate goal. So let's compare this equation with this equation. If I compare them, then I notice that, I'm sorry, with the denominator, with this equation. So compare this, compare with this. Let's compare. So let's notice I have a 1. And I have the coefficient of S squared is theta 1, theta 2 is equal to T1, T2. But I also have that theta 1 plus theta 2 is equal to T1 plus T2 plus K1 over K2 times T1. So let's notice that the product is the same, but the sum of theta 1 and theta 2 is bigger. So let's see what that says. Let's say my product was 16. So for example, if the product was 16, then the factors, and let's just take whole numbers. This could be 4 times 4, or 2 times 8, or 1 times 16. Obviously, I could have non-integral ones as well. But I just want to make a point here. The first point I want to make is if these two happen to be the same, if they're very close together, so here they're close together, and the sum is 8. Here, 2 plus 8 is 10. And here, 1 plus 16 is 17. So what does that tell me? That tells me, it hints, that if the numbers are closer together, the sum is going to be smaller. And when the sum is bigger, the factors are further apart. So this hints that if sum is bigger, that corresponds to factors further apart. Well, let's see what we can do about that. Let's look at the discriminant of this guy. Let's look at the discriminant. squared minus 4ac. So that's theta 1 plus theta 2 squared minus 4 times 1 plus theta 1 theta. And by the same algebra, this is theta 1 squared plus theta 2 squared minus 2 theta 1 theta 2. I'm sorry, plus 2 theta 1 theta 2 minus 4 theta 1 theta 2. So that's going to be theta 1 squared plus theta 2 squared minus 2 theta 1 theta 2, which is just theta 1 minus theta 2 squared. So theta 1 minus theta 2 squared is the difference, square of the difference. Obviously, if they're further apart, the difference is going to be bigger than if they're close together. So let's compare that with the discriminant here. So this thing, theta 1 minus theta 2 squared, and let's see what that is. Okay, so this thing is, not what I want to do here. Okay, so we had calculated actually what the discriminant is. That's equal to this thing. This is equal to T1 minus T2 squared plus K1 over K2 T1 squared plus 2T1 plus T2 K1 over K2 T1. We calculated, here's the discriminant. I just copied it. So you can see that theta 1 minus theta 2 squared is bigger than T1 minus T2 squared. It's bigger than T1 minus T2 squared. So our intuition from here is actually correct. The difference, if this is true for the square, it's also going to be true for the magnitude. So for the magnitude of theta 1 minus theta 2 is greater than the magnitude of T1 minus T2. That way I don't worry about the sign. So that says the difference in magnitude between theta 1 and theta 2 is bigger than the difference in magnitude between T1 and T2, just like we saw here. So what does that mean? What's the upshot? Remember, the zeros of the denominator, when I do the inversion, they come in the exponent. So recall, in the inversion, the thetas come into, I get things that look like e to the minus t over theta 1, e to the minus t over theta 2. I get terms with coefficients that I add up that look like this. For the interacting. For non-interacting, I get e to the minus t over t1, e to the minus t over t2. I get terms with coefficients, but the time dependence is e to the minus t over t1 and e to the minus t over t2 when they're non-interacting. But when they're interacting, it's e to the minus t over theta 1 and e to the minus t over theta 2. So, if the thetas are further apart than the t's, like 16 and 1 instead of 4 and 4, then that tells me that one of the thetas is going to be bigger than all the t's. Here it's T1 and T2. So what does that mean? That means, remember, e to the minus t over T1 decays if I plot e to the minus t over t1 versus t, here's 0, this is 1. T1 is the time it takes for this to decay to 1 over e of its initial value. So this, if these numbers are smaller than, say, theta 2, that says that these decay pretty quickly in 1 over t1 and 1 over t2. If one of the thetas is much longer, we're going to say theta 1 is the big one, then that one is going to take a hell of a lot longer to get there. So what does that mean? That means that if I have a change in the input, x prime, or a change in what's coming in from the right side, the system is going to respond slower. It's going to take a lot longer for it to get where it's going because it has a time constant that's much longer. So what does that tell me? That tells me that interacting systems are more sluggish than non-interacting systems. Things just take longer to shake out than non-interacting systems. And those are things we have to think about. If we have a disturbance to our plant, we don't want it to take a week for that disturbance to shake out. That's a relevant consideration. Are there any questions on that? So the whole point of this derivation was not only to show you what G tilde was, G tildes, but also to come up with that very relevant factor, is that when things interact, it takes longer for things to shake out. Even in a case where things stay stable. There could be other situations where they don't stay stable. In this one, they stay stable. It's still stable and over down. Even in that case, the interaction is sluggish. It makes it take longer. Questions? Okay, so let's look at non-interacting with dead time. First order. With dead times. Now, dead times. Dead times are delays. But in this class, when we looked at plug flow reactors, we always assumed that the plug flow reactors didn't have any reactions. Why is that? Because once you put reactions into the plug flow reactors, they're no longer linear. So we kept plug flow reactors as really boring. They're just pipes with no reactions in them. And if they're plug flow, well then what comes in just takes a while to come out, but there are no changes. So we consider the delays in this class, if you don't have reactions in the plug flow reactors, that's just plug flow reactors. So, and we think of the usual CSTRs as our typical first order system. So when I say first order systems with delays, I'm thinking of mixtures of plug flow and CSTRs where there's no reaction going on in the plug flows. Okay, so each one of them has a G tilde. Each one of those systems has a G tilde that's a first order system, API, over 1 plus STI. That's the CSTR part. And then I've got the dead time part, E minus S theta part. dead type. And if they're non-interacting, then I know if they're non-interacting, I just multiply them together. It's not like the interacting one. Non-interacting is where all the information goes from left to right. So G overall is the product on KPI 1 plus SPI times e to the minus, well, so why don't we write this, right? Times the product on J, e to the minus S theta. I separated them out for no particular reason. Actually, I could just leave them in. I don't have to do that. And just to get a sense of what might be going on here, I want to notice that we call the Taylor series. If I have a Taylor series for e to the STI, well, that's equal to 1 plus STI plus STI squared over 2 factorial plus STI cubed over 3 factorial plus 9. And if I only look at this to linear order, so for small s, small STI, meaning less than 1. Now let's think for a second, what am I talking about there? For small st1, that means I'm kind of looking at what's going on when s goes to 0. S is much less than 1 over t1. S goes to 0, remember, tells me something about long times. Remember the final value theorem, I was taking the limit as s goes to 0 of s times y prime, of s times y prime of s, y prime tilde of s. So s goes to 0 tells me something about long time. So this says I'm not looking at, at 2 short times. Then e to the STI is about equal to 1 plus STI. Meaning, since STI is much less than 1, S squared TI squared over 2 is going to be much less than STI, so I can be like that. In that case, each of the 1 over STIs, 1 plus STIs in the denominator, looks something like an e to the STI. And e to the STI in the denominator is like an e to the minus STI in the numerator. So this tells me that G tilde overall of S looks sort of like pi I of the KPIs times e to the minus S times the sum of the theta j's plus tj's. How did I get that? Each one of these looks like an exponential in the denominator. I can move the exponential to the numerator by putting a minus sign. And if I take the product of exponentials, I get e to the sum of the exponents. And here's the sum of the exponents. And I separated out the I part from the exponential part. So what does this say? This is the product of the steady-state gains. The overall steady-state gain is just the product of the individual overall. Product of the individual steady-state gains. But when I have first-order systems and time delays, it kind of looks like a much longer time delay. Looks like an effective time delay. Of not just the sum of the theta j's, that is the intrinsic time delays, if you like, plug flow reactors, but also the T's for the CSTRs. So it looks like that's much lower. So it looks like each of the first order systems is making the delay longer. So again, this is going to be sluggish. It's going to take longer for things to happen. It's like there's a longer time delay. And let's think physically why that's the case. It's always good when you do mathematics to take 2 steps back and say, what the hell is he talking about? What does that mean physically? Well, obviously if I have a blood flow reactor with no reaction, and I have a step function coming in, then it's going to, at time t is equal to 0, I'm going to see a step function coming out at a time t is equal to tau. Before t is equal to tau, I'm not going to see anything. Is that clear? How about if I have a CSVR? If I have a step function coming in, I see something immediately coming out. But it doesn't reach its steady state, or it doesn't even its rise time until it rises, essentially 1 over e times the total rise in roughly an amount of time t. So even though it's not translating a step to a step, I don't see a